Hey, how you doing? Welcome to Classical Mechanics. So we have studied the simple harmonic oscillator and also the damp harmonic oscillator. In each of those cases we had homogeneous linear differential equations. This means our differential equations to describe the physical system were linear in the derivatives and there were no independent terms. Let's go one step beyond and remind how to solve the inhomogeneous linear differential equation. Then we will go to the physical realm and with force harmonic oscillator, and we'll use this equation and its solutions. Then we will show how to solve almost any realistic external forcing applied to any harmonic oscillator. What we're doing here is a key point in physics. So let's start by considering the following differential equation. On the left hand side we have our now old friend, the damped harmonic oscillator. On the right hand side we have this exponential term. The exponent is imaginary, yes, which does not look very physical, but do not worry about that and get used to seeing lots of complex math in physics. Although we cannot measure any imaginary magnitude in nature, its maths are very useful to get to the measurable, real magnitudes. How do we solve this differential equation? Well,
make an educated guess.
We have to guess a solution. From what we've seen so far, I'm going to guess an exponential such as x equals to a times e to the I omega t. To check whether this is a solution, I will derive it once and twice and substitute into the differential equation. X two dots plus 2 gamma x dot plus ax equal to ce to the I omega t. Let me remove the exponential. Let me factor out a and solve for a. This is what has to be a so that my guess solution is solution of the original differential equation. Let me substitute it in full into my guess solution. So this is a particular solution to the differential equation. From your course in calculus, you know that the general solution to the differential equation is the homogeneous solution plus the particular solution, one particular solution. So this is a bit long, but it's the general form. Now let's think for a while that the inhomogeneous function can be written as the sum of two terms, c1 e to the I omega 1 t and c2 e to the I omega 2 t. Using the superposition principle, the solution to the differential equation would be one particular solution for the first term plus one particular solution for the second term plus the homogeneous solution. This way we can write the solution to any sum of inhomogeneous functions written in terms of e to the I omega t. Now let's pause here for a bit and talk about a very powerful concept in calculus, the Fourier series. We can write any periodic differentiable function as the sum of sine and cosine functions. This statement is very powerful. We won't demonstrate it here, but let's pay attention at its meaning. Imagine any weird periodic function. This says that you can make a series of sines and cosines, probably infinite, that added together make that weird periodic function. If we need a discrete number of sines and cosines, we can write a summation. If we need a continuous distribution of sines and cosines, we will write an integral. This is very good because once you know how to solve a problem for a cosine, using superposition, you know how to solve a problem for almost any well-behaved function. So any function can be generated by adding together simple harmonic motion. Isn't that cool? There is a very nice video on YouTube that makes this concept very visual. Check it out. Now let's go back to where we were. We have the solution to a differential equation that is that of the damped harmonic oscillator plus an inhomogeneous term. And because we can write any well-behaved function as the sum of sines and cosines, this inhomogeneous function can be anything we want, because we can write it as sines and cosines. Okay, let's go back to physics. Let's go back to the damped harmonic oscillator and let's put external force in. What kind of force in do you want to put? Well, because almost any interesting forcing can be written in terms of sines and cosines. And because a cosine is basically a phase-shifted sine, let's put a periodic force in. Let's have this forcing be a cosine. Does it make sense? Alright, now I want you to think about all this, check that other YouTube video, and in the next lesson I will solve the forced and damped harmonic oscillator. May the science be with you.